Direct Isoparaffin Synthesis from Syngas by Anita Boy, Bao Ma, Catriona Johnson, and Raquel Garcia. An overview of this project includes the introduction where the problem is defined, the method chosen where approaches taken are described, our results and discussion, and finally conclusion where we define and answer the importance of the findings. What is isoparaffin? It is a branched chain with its primary function as a thickening agent and is mostly known for its use in alternative fuel and cosmetic products. Isoparaffin is directly synthesized from syngas. The project's goal was to design an industrial-scale reactor, which in this case was a fixed-bed catalyzed reactor. At the very bottom, we are able to see our overall reaction. The method of the reaction occurred in a fixed-bed catalyzed reactor that took place during the supercritical phase with an inert medium of N-butane. This helped directly synthesize the isoparaffins in a one-step reaction. The chosen catalyst was cobalt silicon dioxide and the zeolite HSZM5 at a 2:1 ratio. For the conditions of this project, the temperature is maintained at 533 Kelvin with a total pressure of 5 megapascals. Two approaches were taken in order to find the best temperature and the unwanted products of this reaction. An energy balance model was calculating the conversion percentage based on the increase of temperature to discover which temperature was most efficient. The selectivity model was calculating the selectivity based on the temperature increasing. With this model, the unwanted products are displayed on the selectivity percentage. The outcomes are modeled using different catalyst ratios from the data collected of Table 2. This is to determine the best catalyst ratio for the reaction. The outcomes were also modeled by using different reaction mediums to determine the best reaction medium and the difference between the regular and hybrid catalysts. The table displays the conversion of carbon dioxide and percentage selectivity of various reaction products of different mediums with catalysts cobalt silicon dioxide and HZSM5. In this case, the catalysts used instead contained palladium silicon dioxide. The table displays conversions not as high as the reaction using cobalt silicon dioxide and HZSM5, but the value still displayed to supercritical butane as the better medium. Different sources can be used to compare our results for the conversion of carbon dioxide. The table 3 shown below now compares the different zeolites. This table 6 displays the effective pressure that was examined. This reaction that took place was not under supercritical conditions. Table 3 on the left displays the influence of reaction temperature on FT synthesis using hybrid catalysts. The graph on the right displays the effective temperature on carbon selectivity. It can be noted that around 533 Kelvin, the selectivity of isoparaffin is at its highest. With a higher conversion percentage, the choice of the catalyst was the cobalt silicon dioxide containing the zeolite HZSM5 in a 2:1 ratio. The cobalt silicon dioxide produced a small amount of wanted isoparaffin. However, the addition of the solid zeolite catalyst raised the selectivity of isoparaffin exponentially. Some studies display that with the zeolite, the selectivity rises from 3.1 to 21.7%. Butane at supercritical conditions displayed the best choice for an inert medium. The choice of the inert medium maintained the lifetime of the catalyst used, as well as produced a higher amount of isoparaffin selectivity. The ratio for our chosen catalyst, 2:1, received the highest percent conversion of isoparaffin with 12% conversion. The graph displays a greater percent selectivity for isoparaffin with the catalyst as a 2:1 ratio compared to the catalyst with a 1:1 ratio. We can compare the inert mediums, helium and supercritical butane. Supercritical butane gives the higher percent conversion of isoparaffin of 23.3% compared to helium of 16.8%. Looking at the graph below, we can see that supercritical butane once more gives a higher selectivity percentage for the isoparaffin compared to helium. Here we can see the effects of pressure on our reaction. Table 3 gives us percent conversions under the conditions of 5 megapascals. We are able to see the higher percent conversion and hydrocarbon selectivity percentage compared to Table 6. The graph compares 5 and 1 megapascals for selectivity and conversion. We are able to use the material balance in order to find some of these calculations. With the weight over the molar flow rate of syngas, we are able to find our cobalt silicon dioxide of 0.5 grams. Our syngas to butane ratio is 1:4. Cobalt silicon dioxide contained 10 weight percentage. With that ratio of 2 to 1 to HCSM5, we are able to find the weight percentage of HCSM5 of 5%. We continue this material balance with the weight of syngas going in as 0.85 grams and the weight of butane going in 3.4 grams. The following material balance gave us the weight of carbon dioxide going in as 0.2833 grams and the weight of hydrogen going in as 0.566 grams. We can now calculate the exit of N-butane and carbon dioxide as 3.4 grams and 0.046 grams respectively. To help us with the material balance, we are going to use the selectivity given for methane, olefin, paraffin, isoparaffin, and carbon dioxide to find the mass of each of the products. 83.7 weight percentage of carbon dioxide went into the feed. Selectivity is the weight of the exit product over the weight of the whole product. This was based on the weight in selectivity in regards to carbon dioxide, so hydrogen was not included. At the bottom, we are able to see the selectivity values we have gotten. We were able to use MATLAB to create a user-friendly code to solve for exit weights. On the left, we are able to see the output of each exit weight. This was a result from our MATLAB code. The initial weight over flow rate of syngas is 10 grams hour per mole. The initial weight of syngas calculated material balance is 0.85 grams. To solve for this flow rate, we need to use the following formula. Using the rate law and the flow rate, we can solve for our rate. Integrating the two, we are able to get 48.13 mole gram per hour for our rate. To confirm 533 Kelvin would be a good temperature for this reaction, we were going to plot temperature versus conversion. The graph displays that conversion is no longer increasing significantly at 533 Kelvin. Through our results, it is evident that the best way to conduct a one-step syngas to isoparaffin synthesis is using Fischer-Tropsch at 533 Kelvin, 5 megapascals with a 2 to 1 ratio of cobalt silicon dioxide to HCSM5. We have been able to prove this through the analysis of this reaction taking place with different temperatures, pressure, catalyst ratios, and inert mediums. Data that has been collected, modeled, and analyzed from the multiple sources has led us to this conclusion. Thank you for listening.